All right, lesson 3.8. So we're looking at the tangent function today. Specifically, the things that we're going to go through today is graphing. But before we get there, I want you to remember this, that with trigonometry, this is lesson 3.2, I believe, that sine is equal to what ratio? Sine is y over r. What was cosine? That's right. And if sine is y and cos is x, tangent is... Okay, now we went over that on lesson 3.2. What I want to point out as well, though, if sine is y and cosine's x, we're going to see pretty soon that sine is tangent is the same thing as sine divided by cosine. And it's very important you understand, that's called an identity. It's very important that you learn that, okay? So sine is y, cosine's x, tangent is y over x. You got it. All right, let's begin. Oh no, am I frozen out? There we go. So here I have some information just to kind of walk you through what I was just saying about, since tangent is y over x, that it's going to become sine over cosine, and cosine cannot equal 0. If it does, you have what's called an asymptote. So on your drawing, here's what I want you to do. We're going to add in some asymptotes. Tangent's going to look like, I'm just going to add 2 asymptotes to the right and 2 evenly spaced asymptotes to the left. Tangent's going to look kind of like, that's probably too close. Sorry, let me move that one over about right there. Tangent looks like an S curve, not just a S curve. It looks like a whole bunch of S curves. So I have 2 asymptotes to the left, 2 asymptotes to the right. I want you to connect those with S curves. Like this. So there, right there was one S curve. What you would do is you would just have multiple of these S curves. I'm just, for the sake of brevity here, because we're going to graph these quite a few times, I'm just going to copy and paste. And the reason I'm going to do that is because it's going to help me on my...
You want to go past?
Nice, go. I can realign my asymptotes to make mine look right. But since if you draw yours in, you can just kind of make them fit as best you can. This way, mine will look a little bit more uniform if I copy and paste. So I'll do it like that. Let me get that right there. There you go. That's what the tangent function is going to look like. Okay, so tangent, it is the ratio of the y to the x. That means tangent is y over x. You know, I should have wrote that in right there in the notes. Let's just write it one more time. It is y divided by x. Anytime x is 0, you have these asymptotes. So if you think through the unit circle, where does x equal 0? X equals 0 at pi over 2. So that's that asymptote right there. X is equal to 0 again at 3 pi over 2. That's where this vertical asymptote would be located. On the negative side, we would have a asymptote at negative pi over 2 and at negative 3 pi over 2. You might notice, if you're thinking critically as you're drawing here, that these are not 2 pi apart from one another. Tangent's period is not 2 pi like sine. Tangent's period is 1 pi. Tangent's period is 1 pi. The period for tangent is 1 pi. So just a reminder what that period means. From the start to the finish, which with sine and cosine, we'd say max to max. But tangent will not have a maximum because it approaches infinity, nor will it have a minimum because it goes to negative infinity. But that period there is 1 pi from asymptote to asymptote. Something also that's unique about tangent is every graph of tangent will only increase or it'll only decrease based off of whether it's positive or negative. Look at this graph carefully. This graph, what can you tell me about this graph right here? It's increasing. When you have a break there, you wouldn't call this a decreasing break. The graph broke, and when we start back over, it's increasing again. This tangent function I just showed you is only increasing. All right, so let's look at some examples today. I don't want us to forget how to use the hand trick. So the first slide, we're going to fill in our data on this table using our hand trick. It tells you the period of the tangent function is 1 pi. Therefore, it'll complete 1 full cycle on the interval 0 to pi. However, there's a vertical asymptote at pi over 2, as we'll see with our hand trick. So looking at your left hand, it says make a table of values x, y if on y equals tangent x on the unit circle. So here we go. If we were going to find the value of tangent at 0, which finger would you bend for 0? Pinky. Bend your pinky, flip your hand over. Now, tangent is the y's over the x's. How many y fingers do you have above your pinky? 0. So it's square root 0 divided by square root 4. Now, that can simplify, and that will become the value 0. Now let's go to pi over 6. Which finger do we bend this time? Ring finger. Bend your ring finger. Flip your hand over. How many y fingers do you have above the bend? Just 1. How many x fingers do you have below your bend? 3. That can reduce. If you remember, you shoot the square root up. Basically, you multiply by a funny looking 1. I'll write it over here. You would do the square root of 1 divided by the square root of 3, and you'd multiply by square root of 3 over square root of 3. It's equivalent to shooting it up. In the numerator, you get the square root of 3. Denominator, we get the square root of 9. Square root of 3 times square root of 3 is square root of 9. What is the square root of 9? So you can write this value in as square root of 3 divided by 3. Okay, move on. Pi over 4. Which finger do we bend? Middle. Bend your middle. Flip your hand over. What do we get? Square root of 2 divided by square root of 2. That can reduce and becomes 1. Okay, pi over 3. This time it's our index finger. We bend that finger. We flip our hand over. How many fingers above the bend? 3. How many below the bend? 1. You can probably see the pattern. What's happening to the y's each time? They're increasing by 1. What's happening to the x's each time? Decreasing. This simplifies just to become the square root of 3. The square root of 1 is 1. Dividing by 1 does nothing. So it's just square root of 3. Okay, now pi over 2 is where we get our first problem. Pi over 2 is our thumb. You bend your thumb, you flip your hand. I have the square root of 4 because I have 4 y fingers, but I have 0 x fingers. Are you allowed to divide by 0? No. This creates that asymptote. I want to remind you, you don't ever say it's equal to undefined. So I'm going to draw an arrow through it, and then I'm going to say that's undefined. That would be that vertical asymptote I just showed you on the previous slide at pi over 2. But just because it's undefined does not mean I need to change my pattern. My pattern should stay the same, meaning the y's, they increase up to 4, and now they start to decrease. My x's continue to decrease until they get to -4. I'm just going around the unit circle. What we are on the unit circle, where we're at, if you're tracking, if you're able to think through multiple things at once, what we just did is we moved up around to pi over 2. And so now when we start approaching pi, you'll notice the x's are going to turn negative while the y's start to decrease. They're still positive, but they decrease. That's where we are now. So here's what's going to happen. 2 pi over 3, which finger is that? 2 pi over 3 would be the index finger. Bend your hand, flip your hand. Bend your finger, flip your hand. Notice you now have square root of 3 for y. And x, how many fingers do you have? 1. And it's technically a negative square root of 1. The x was negative. So my y's count up to 4. Now they're going to count down to -4. My x's have counted down from 4, and they're going to continue counting down until they get to negative square root 4. This reduces to become negative square root 3. 3 pi over 4. Which finger do we bend? Middle, bend it, flip it. The y's are counting down now, so I get a square root of 2. X's are counting down. I get a negative square root 2. What's square root 2 divided by negative square root 2? Just -1. Just -1. 5 pi over 6. Ring finger. Bend it, flip it. How many y fingers? 1. X's are negative square root 3. We've had that. We've simplified that. We get square root of 3 over 3 when it's positive. So we'll now get negative square root 3. I'm going to just put the negative in the denominator. Square root of 3 over -3. Okay, and last one to complete our period. Pi. Which finger would you bend for pi? Pinky. Bend it, flip it. Y's have now counted down to 0. The x's have counted down to the negative square root of 4. That's 0 divided by negative 2. What's 0 divided by negative 2? 0. Now, when you look at this table, it looks like the values were getting bigger and bigger, and then all of a sudden they got smaller, but that's not how it works. Remember what I just told you on the previous slide. Tangent always increases or it always decreases. What happens is it's increasing, state where it's increasing. It increased from the interval where we started at 0 up until pi over 2. And that's when it becomes a vertical asymptote. A vertical line is like an infinite slope. So I do a parenthesis. I can't actually increase to it. So I do a parenthesis. And technically when you're doing increasing, you don't ever do brackets. So I should just do parentheses on both. I increase from 0 to pi over 2. And then there was a break. The undefined is a break. That's a union. That's where you would do a U. Starting after the pi over 2, I continue to increase, but now I'm increasing from negative numbers. So I increase from pi over 2 all the way to pi. Now that's from part A. That's where I increased on part A. I increased from 0 to pi over 2, union pi over 2 to pi. I always increase. There was just a break right there in the middle. Just okay. Something I want to show you though. We're going to learn in the coming lesson that there's a better way to define tangent, and it's not on this interval. In the future, we're going to say it's increasing like this. We'll say it's increasing from negative pi over 2 to positive pi over 2, because if you use that interval, you don't have to, that's between the asymptotes. Let me go back a slide. Let me go back one slide. From negative pi over 2, that was here, to pi over 2. You see how there's no break in between? In the future, we're going to call that the period of tangent. On that example we just did, we looked at this interval. Watch my green line. We looked from 0 to 1 pi. That's where we looked. And so you saw this half of the tangent curve, and then you saw this half of the tangent curve. But what we're going to do in the future is we're going to say, let's look at it between negative pi over 2 and positive pi over 2, because we get a full period without a break. So that's how we're going to look at it in the future. Does that make sense to you? The function, does it increase or does it decrease? Tangent here, without a transformation, always increases. It never decreases. No decrease. Let's do that. No decreasing interval. I'm going to add that in right before we move on. Okay. So now we're going to use those points that we just had. I'm going to show you how we're going to graph. So now let's look at part C here. Graph the function using the values in the chart from part A. Well, we had an asymptote. You know what? Let's first figure out what this is counting by. It's labeled here pi over 3, 2 pi over 3, 1 pi, 4 pi over 3, 5 pi over 3, 2 pi. But that's not what it's counting by. What is halfway from 0 to pi over 3? What is half of pi over 3? That's what this spot is right here. I'm going to erase this in a second. It's pi over 3 divided by 2. That is pi over 6. We are counting by pi over 6s. Okay, so call out the values. I can't go back and forth because you'll get sick watching me do this back and forth, back and forth. Well, I know we started at 0, 0. We had that point at 0, 0. What was the next point from our table on the previous slide? It was pi over 6.
Pi over 3.
It was pi over 6. That's the x. Look at the table. This is x. This is y. Sorry. So 0, 0. That was my first point. My next one is pi over 6, comma, square root 3 over 3. Let's figure out what that is real fast. Where's my calculator? Square root 3 over 3. Let's get that as a decimal. What is calculator square root 3 divided by 3? That is 0.57. Let's just say 0.6. We're going to graph that approximately 0.6. Okay, so here we go. We're doing pi over 6, comma, 0.6. All right, pi over 6, comma, 0.6. What do y'all say about right there? If this is a half, that's a whole, maybe right in there. Okay. Then we had pi over 4. Pi over 4 is halfway. I know it sounds weird. It's halfway between pi over 6 and pi over 3 is pi over 4. It's directly in the middle. I know it seems strange, but it makes sense if it's in degrees. In degrees, this is 30 degrees. This is 60 degrees. How many degrees is in between 30 degrees and 60 degrees? 45, which happens to be pi over 4. So this right here, the halfway point is pi over 4. What did we have on our previous table for pi over 4? 1. So plot that point. Pi over 4, 1. What did we have for pi over 3? That was our next point. Square root of 3. I believe that's 1.73. Let's do that. Square root of 3. 1.73. Yes. 1.73. For later, I'm just going to plot these on so we have them. So we can look at it. I think those are our only strange values that we'll have to look at. Okay. So at pi over 3, we're going square root of 3, which is 1.73. That's just about halfway through. And then you're going to have your asymptote. This would be pi over 2. How do I know? Because we learned they're counting by pi over 6s. That's 1 pi over 6, 2 pi over 6, 3 pi over 6. 3 pi over 6 reduces to become pi over 2. So do an asymptote there. Now remember what I told you. What's the period of tangent? It's 1 pi. So if we go another whole pi, we should have another asymptote. I'm going to go ahead and put in all the asymptotes. Now I know that. So that if I go one more whole pi, so that means since it's counting by pi over 6s, I need to go 6 blocks. So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4, 5, 6 pi over 6. This is another asymptote. Go ahead and put an asymptote right there. Let's see if we have space on our graph for this asymptote going this way. 1, 2, 3, 4, 5. Oh, I basically can. Let's go ahead and put an asymptote right over there. So the labels, this would be x equals pi over 2. This is 1 whole pi added. So with a common denominator 2, this would become 3 pi over 2 because I added 2 over 2. I added 2 in the numerator since that's the denominator. So 1 pi over 2 became 3 pi over 2. This would be subtracting 2. So this would be negative pi over 2. Okay, so we have those points. And the other points we had, what do we have starting at 2 pi over 3? What was our value there? Negative square root 3. So negative 1.73. So negative 1.5, negative 1.73, somewhere in there. We had a pi over 4 in the middle, which would have been a negative 1. That's pi over 4. And then we'd have here, this would be 5 pi over 6. 5 pi over 6. And what do we have for negative 5 pi over 6? Excuse me, 5 pi over 6, we had, is it going to be negative square root of 3 over 3? Okay, so that's going to be right in there. So that's the values we had from our table. So if I connected my function, the graph would look like this here, and then over here it would look like that up to pi. Oh, I forgot to put pi on there. Pi, we should have had 0. And you can kind of see how the rest of the graph works. So the rest of today, once we get a few of the points on, we're going to quickly approach the asymptotes. That's what every graph does. That's what an asymptote is. It's a graph. It's a part of the graph. Excuse me. An asymptote is not part of the graph. It's where the curve approaches. It doesn't actually get there. So I'm just going to do it quickly here, like this, just to make sense of what's going on. And it would do the same thing going that way. Same thing going here. So I'm going to just fill that in today as we go. So now on part D, I'm going to come back and I'm going to give us something that I just mentioned on the previous page. When you look at this graph, the interval I gave you from part A was not a continuous interval. From part A was not continuous. There was the break right in the middle of it. So on here, I've shown you 2 continuous intervals. This is a continuous interval right here. That is a continuous interval. Continuous interval. This right here is also a continuous interval. What's the continuous interval that you'll be using in the time to come? We're going to use from negative pi over 2 to positive pi over 2. Whenever you do intervals, you're listing x values. I'm going to make sure I make a note of that too. X values. So we just had a test where we had to write out intervals. A lot of you were doing x comma y's as an interval. You don't do that on an interval. You only use x's. If it says the word interval, you only use x's. If you wanted y's, they would say either, if they wanted x and y, they would say coordinate point. Or if they only wanted y, they would say range. But if it says interval, you write it like you would a domain, except you don't use brackets, you just use parentheses. I could put in an or here since I wrote it twice on the, or you could say this is pi over 2 to 3 pi over 2. Pi over 2 to 3 pi over 2. That's also shown on the graph, but we'll use negative pi over 2 to positive pi over 2. Okay, that's the general overview. Let's get down to graphing it when it's not just the parent function of tangent. Let's do some transformations. Those are Clipper packet. The first slide gives you some, I guess, the rules for finding your 5 key points. There are 5 key features. Honestly, I could have written this in 3 steps. Step 4 just says basically to repeat itself. I'm going to do that within steps 1, 2, and 3. It's going to be a 3-step process for us to find our key features. Our 5 key features are this. We're going to have a left asymptote, that's 1. A right asymptote, that's 2. We'll have a midpoint, that's 3. Then I'm going to call these 2 A points. In between points to help us figure out the A rock, if you will, or slope of the curve. Then we're going to plot those. It's 5 things. It's going to go really fast. It's just repetitive. Okay. So here's your notes to look back at later, but I'm just going to walk you through as we go. So here we go. First, let's graph the function f of x equals negative tangent x. It says state the period and show all asymptotes. The previous slide, here's how it says to do it. It says step 1, find your asymptotes. So what you do is you take what's called the argument. You take the inside. This is the argument. You hear me say that is the argument. You take what's on the inside and you set it equal to the parent function's 2 asymptotes. We're going to set x equal to pi over 2. And you can also set it to 3 pi over 2. I'm going to use negative pi over 2 because it's just easier numbers. You set the argument, whatever your argument is, equal to those two values, pi over 2 and pi over 2. So it's argument equaling, I'll just write that out right here. Argument equals plus and minus pi over 2. Now this one has nothing to solve. You see how there's no value with x? Since there's nothing to solve, we'll go ahead and plot that. Go ahead and put on your asymptotes. At positive pi over 2, draw an asymptote. At negative pi over 2, draw another asymptote. Kevin. Just shut it. Okay, how many lines apart are these 2 asymptotes?
3.
1, 2, 3, 4. So now that we know the spacing, that's the period. Go ahead and add other asymptotes. Every 4 lines, add asymptotes. 1, 2, 3, 4. There's an asymptote. This is technically, I'm doing step 4 repeating right now. I'm going to go this way. 1, 2, 3, 4. There's my other asymptote. And I run out of space. Step 2, the midpoints. The midpoint. You could say the period minus period divided by 2 if you wanted to write it out. I'm just going to say x, comma, and then I'm going to put a d. Now, what am I saying with the x? Or maybe I'll just do a blank. Blank, comma, d. The d is the height. The blank represents being in between the midpoints. Okay? So on this one, what is my d in this equation? Do I have a d at all? No. So on this problem, d equals 0. So my midpoints are going to be something, comma, 0 all the way down. So in between each asymptote at a height of 0, put a dot. So I'm getting one at negative pi. I'm getting one at 0, 0. I'm getting one at pi. And I would get another one at 2 pi, as well as negative 2 pi. So those are just midpoints. Why do I call them midpoints? Ruby, why do you think I call it a midpoint? Just take a wild guess. Why do you think I call it a midpoint? It's in the middle. That's all it is. It's in the middle at a height of d. Okay, last. The third and final step for creating this is what I'm going to call the A points. Whoops, I did it backwards. A points. Now, what do I mean by the A points? We're going to split this difference again. But this time, there's going to be 2 points. You go onto the left. You're going to take your whatever that d value is, which in this case is 0. And we're going to add and subtract an a. So here's what I'm going to do. D plus or minus a, which in this case, we already know d is 0. What is our a on this problem? Remember, that's the front. What's our a? Negative 1. So here's what this means. You go to your points, and you're going to split the difference again. When you go to the right, you do exactly what A says. So as I split these 2 points, the midpoint and this asymptote, as I split the 2, that point's right here, I obey A going to the right. So A is a negative 1, so I go down 1 and I place a point. When you split it going left, though, you do the opposite. So instead of going down 1, guess what I'm going to do? I'm going to go up 1, and I'm going to do that all the way through. So from the midpoint, if I go to the left, I do the opposite of A, which means I go up 1. If I go to the right to split the difference, I obey A, which means I go down 1. So there's that point. And so you do it all the way across. You just repeat them all the way down. I'm going to run out of space there, but I'd have a point somewhere over there. And like that. Now, once you have that, you connect all your dots. Tangent should be what kind of curve? S curve. So follow your asymptotes, connect your dots like that. They always follow the asymptotes. That's the whole point of an asymptote, is they follow it. Like that. Now, what is our period this time? How far apart is each asymptote? It's 1 whole pi. For tangent without a transformation, it's 1 pi. The formula for this is it's pi divided by b. The formula is pi divided by b. What's our b in this problem?
0. Wait.
Not 0. It was not there. It's in front of x. It's 1, which means our period is pi. Our period would be pi on this problem. I'll go ahead and write that in like this so you can see it better. That is a period of 1 pi. So this tangent function, did it always increase? No, this one always decreased. What made it decrease? Negative on the front. Okay, so right now I know it's a lot of information to take in. The best way to get it to sink in is to try to go faster. And so I want to walk you through those same 3 steps. a few times here. So let's try this one all over again. I'm going to start with part A, number 1, asymptotes. Remember, for your asymptotes, you take the argument and you set it equal to plus and minus pi over 2. What's my argument this time? It's not just an x. What's my argument on this problem? Pi over 4x. So put pi over 4x equals positive pi over 2. And then do pi over 4 x equals negative pi over 2. That's what we're going to solve to get our 2 asymptotes. Now we're going to get our reciprocals down this chapter, or the rest of this unit, because we're going to be doing this a lot. To solve this, right now I am multiplying by pi and dividing by 4. That's pi over 4, multiplying by pi, dividing by 4. What's the opposite of multiplying by pi and dividing by 4? Well, it'd be its reciprocal, multiplying by 4 and dividing by pi. That's what I'm going to do here. And so when I simplify that, the 4's cancel, pi's cancel there. What's 4 divided by 2? 2. I'm going to have an asymptote of 2. And before I move on, I'm going to do the same math down below it. I'm going to multiply by 4, divide by pi. Multiply by 4, divide by pi. 4 divided by 4 is 1. Pi divided by pi is 1. So it's 1x equals negative 2. All right, so now let's go add these in. I'm guessing if you're thinking on it, you've probably figured out what the period is without even doing any equation stuff. If you know one asymptote's at positive 2 and you know another's at negative 2, what's our period? 4. We can go ahead and put the period in. Our period's going to be 4 this time. That's our period. It's 4 units. Go ahead and write that in. Okay. Now that was step 1. We got our asymptotes. Can we fit any more asymptotes? 1, 2, 3, 4. Oh yes, we basically can. Go ahead and add in an asymptote while we're here. 1 there, and then 1, 2, 3, 4, and get one more over here. Let's go ahead and add those asymptotes in. Step 2. Do you remember what the step 2 was? Midpoint. And technically, I guess I should make it plural just because there are going to be a bunch of them here. The midpoints, I do blank, comma, D. What is our D in this problem? When you look on the outside, what's the D? The midline, if you will? 0. Okay, so in the middle of all those those asymptotes, put a point with a height of 0. So at negative 4, comma 0, at 0, 0, and 4, comma 0. Okay, what was step 3? The A points. Now, again, you're going to split the difference. So I'm going to put blank because there's going to be multiple of those. But then you do the D value, which is 0 plus or minus A. What's my A on this problem? I can't quite see. Let me zoom it up. There we go. 2. Which is going to, this is, since that'll simplify to be 0, comma, not 0, sorry, oops, blank, comma, positive and negative 2. And that's because A is 2 while D is 0. That's the reasoning there. So here's what it means. As you go to the right, you obey it from the midpoint. You go to the right, you obey it. Since I go right, the split, I'm going to go up 2. That's a positive 2. I go up 2. But if I went left, I don't obey, I disobey. So I go down 2. Remember how I said tangents like slope? Remember how I said tangents y over x, which is like slope? So that they should always look like a line. Whichever way, they shouldn't look like a parabola or anything like that. They should look like a line. So this one, it's going to go up from left to right. This one's increasing. So go ahead, 2 up, 2 down, put a dot, 2 up, 2 down. On either side, those would be your dots. When you connect them, try to make it an S curve as best you can. So try to make it an S curve as best we can here. Coming from your asymptotes, it'll look something like this. I want to remind you that this concavity here changes. What do I mean by concavity? It was on the left side of the midpoint, it's concave down, then it becomes concave up, which means we have a point of inflection. Every midpoint is a point of inflection. That's something I need to say that I haven't said yet. These midpoints are the points of inflection. Points of inflection. That's going to be important to know as we go on. That just means we're changing from concave up to concave down or vice versa. And this problem, concave down to concave up on every midpoint. Questions over that? I'm going to give you your first DOL. Let's see if you can mimic the 3 steps. See what you come up with. DOL number 1. All right, now let's try to look at some that are a little bit more complex. So starting on example 3, I've introduced on example 2 some transformations. Now let's look at some that are a little bit more complex and see what we do. So example 3a here, it says to graph this function. We're going to walk through the same steps. Steps don't change with complexity. So step 1, I'm just going to write 1, circle it. You take the argument. What's my argument this time? X plus pi over 4, and you set that equal to positive pi over 2. And we're also going to take this and set it equal to negative pi over 2. So what do I do from here? Well, how would I solve for x? We would subtract pi over 4. Now, as it is, I don't have a common denominator, so I would need to multiply by a funny looking 1. To get a common denominator, I need to multiply numerator and denominator by 2. What's 2 pi over 4 minus 1 pi over 4? 2 pi over 4 minus 1 pi over 4 is 1 pi over 4. Now let's do the same thing here. For the second asymptote, we subtract pi over 4. And so I subtract pi over 4 on the right side of the equation since I'm doing it on the left. Again, I need to multiply by a funny looking 1. I'm going to multiply by 2 divided by 2. That's 1. I'm multiplying by 1. Doesn't change the problem, but it does help me simplify. I now have negative 2 pi over 4 minus a pi over 4. What's negative 2 pi over 4 minus 1 pi over 4? Here, 2 people got the right answer. A negative, subtracting even more negative, does not turn it positive. It becomes, that's negative 2 pi over 4, negative 1 pi over 4 becomes negative 3 pi over 4. We're going to add our asymptotes and we'll figure out what our period is. Pi over 4 is half of pi over 2. So that means you're at this first mark right there. And it also means our graph's counting by pi over 4. So there's 1 pi over 4 this way. I need to go 3 pi over 4 this way. How many blocks apart are they? How many units apart, I should say? 4. 1, 2, 3, 4. So that means every time I have 4, I'm going to put another asymptote. So 1, 2, 3, 4. Add in another asymptote. 1, 2, 3. Don't quite make that one. It would be somewhere over here. Like that. 1, 2, 3, 4. I have this one right there. There are all my asymptotes. Coincidentally, what is the length of one period? It's 4 pi over 4. What is 4 pi over 4 is equal to? Pi. Our period's going to be pi here. If you're wondering why is it, it's because the formula is pi divided by b. My b is 1 on this. My b is 1, so pi divided by 1 is equal to pi. That's why algebraically speaking. Okay, step 2. What's step 2? Midpoints. And maybe I should have called those points of inflection. I'll just do MP or points of inflection. Maybe that's a better way of saying it, because mathematically that's what they are. We know we're going to split the asymptotes. So we split the asymptotes. That's my blank here. What's my D on this problem? 0. Again, D is 0. So my points of inflection are each going to occur 2 points away, 2 units away, 2 blocks away, I should say, from any asymptote on the x-axis. So we'd have one more just out there if we don't quite get it. Okay, and finally, step 3. What I call the A points. Again, we'll split the difference. But now I'm going to take 0 and plus or minus what number? -2. I'm going to do not minus on top. I'm going to minus and add 2. So going to the right, I subtract 2. Going to the left, I add 2. So I'm doing this because I subtract going to the right. So from any one point, if you go to the right, you should go down 2 units. Which means if you go left, you would go up 2 units. So it should look like it's a decreasing S-curve is what we should have once we graph all this. So fill in your points all the way down. That would have one there. That would have one just off the graph somewhere right there. And then you can connect them. Again, it's an S-curve. Go from asymptote to asymptote. Whole point of an asymptote, so that's what the graph is supposed to approach. So that was not a very good S-curve there, but like that. There we go. All right. Let's look at part B. So this will be the first time we have a different D value. So part B. Let's check out this graph. All right, step 1. What was step 1? Our asymptotes. So you take the argument and you're going to set it equal to plus or minus 2x minus pi needs to be equal to a positive pi over 2 and equal to a negative pi over 2. So you set it equal to a plus and a negative pi over 2. All right, what will I do first this time? I hear add a pi. Okay, if we add a pi on the left, guess what I got to do on the right? Add a pi. So we don't have a common denominator. Let's multiply by a funny looking one. Let's multiply by 2 over 2 and 2 over 2. So what is pi over 2 plus 2 more pi's over 2? That's 1 pi over 2 plus 2 more pi's over 2 becomes 3 pi over 2. And then here I have a negative pi over 2 plus 2 pi over 2. Just a pi over 2. Okay, good. And then x isn't isolated yet. What's our last step? Divide by 2. So if I divide by 2, I gotta divide this by 2 as well. When you're taking 3 pi and dividing by 2, but then dividing by 2 again, that's the same thing as 3 pi divided by 4. I have 1 pi divided by 2 divided by another 2 becomes pi divided by 4. So pi divided by 4 is halfway to pi over 2. So it looks like I have an asymptote. 3 pi over 4 would be halfway between pi over 2 and 1 pi, if you think of your unit circle. There's one asymptote. You have another asymptote at 1 pi over 4. So this is going to be a really narrow graph. Our asymptotes are every 2 lines. So every 2 lines, you're going to have an asymptote. Oh, goodness gracious. It's a lot of asymptotes we're going to have this time. Every 2 lines. All right, last one. Okay, now that we have all those asymptotes, let's now do step 2, the midpoints, or we could call them the points of inflection. Remember, you split the difference. You split the difference, and then you do a d. What's our d value this time? 2. So split the asymptotes and a height of 2. Put a point all the way across. Those are our points of inflection this time. And then finally, your A points. In this case, we're going to split our difference, and then we'll take 2 and we will add or subtract 3. So splitting the difference, I should go up 3. So 1, 2, 3. Or going left, down 3. 1, 2, 3. Like that. This one's going to be really narrow. Up 3, down 3. Again, at this stage, when you look at it, they should look like almost a diagonal line, like points that would make a diagonal line. Though when we graph it, tangent is always an S-curve. Oh man, there's a whole bunch of these on there. Okay. All right, so we go to connect these. Almost there. All right, let's write in. What's the period here?
1, 2.
It's 2 blocks, which is how far on the x-axis? From it to be pi over 2. Very good. And a way mathematically to get that is you take, what is our b value? Our b is 2. And so it would just be pi over 2. All right, with that, I have a DOL for you. DOL number 2. All right. I'm picking up. Let's now go to example 4. Example 4, here, I want to just kind of make sure you got your rules down more than anything. So this is where you can look back later. So let's start with this. Left asymptote. What I would do, how do you find a asymptote?
The first number.
Argument. The argument equal to pi over 2. If this says left, I should technically set it equal to positive pi over 2, but I'm just going to keep the same pattern I've been doing. Ignore the left and the right. I'm just going to cross that out. I'm going to set it equal to pi over 2, and we'll do the same thing here in a moment. Equal to negative pi over 2. All right, what would be your first mathematical step if it says to multiply the x right now? It says to multiply by 1/2. What's the opposite of multiplying by 1/2? The reciprocal. You multiply by 2 over 1. Multiply by 2 over 1. So here we have those canceling, those cancel. And so I have, let me draw a little arrow so you can see its continuation. I now have x plus pi equals, that cancels. What's pi divided by 1? Pi, okay, now what? We subtract our pi, and when I subtract pi, that cancels and that cancels. So I'm left with 0, x equals 0. There it is, x equals 0. There's our first asymptote. Let's do this again. Same steps. We multiply by 2 over 1. 2 over 1, those cancel, those cancel. Multiply by 2 over 1, those cancel. And I'm left with a negative pi. So I have x plus pi equals a negative pi. Now what? We subtract pi on both sides. It still cancels on the left. This time on the right, it does not simplify. Well, they combine together, but they don't simplify to 0. What do we get? Negative 2 pi. A negative pi and another negative pi make negative 2 pi's. So what's the period? How far apart are these? 2 pi's. It's 2 pi. Now remember, you could use the formula pi divided by b, which means it's pi divided by 1/2. Dividing by a fraction is the same thing as multiplying by the reciprocal. And so you could get 2 pi that way as well. Now here we go. The equation of the asymptotes. Now you haven't seen this yet. We've just been writing them out. Once you know how far apart they are, you take either asymptote, which I'm going to take x equals 0. And what you do is you set it, you add the period with a k. So I'm going to say plus, I'm sorry, with an n. K is usually for the period. The period was 2 pi. So you could just say 2 pi k, or you could do k, 2k pi, however you want to do it. I think this is the way the last test had it written on one of the problems, was like that, where k is an integer. That just means you can find all the asymptotes just by adding or subtracting a certain number of pi's. Where k is an integer, that would be a double looking z thing. It means it could be a positive 1, a positive 2, a negative 2, but it couldn't be a decimal. It couldn't be a half. It couldn't be a something like that. So you take any of your asymptotes, doesn't matter which one. I just took the first, and I added a period with a k with it. That would actually, we could simplify that. What's another way of writing that? What's 0 plus 2k pi? Yeah, you just say 2k pi. I could write it that way. 2k pi. There you go. Points of inflection. Okay, what's halfway between 0 and negative 2 pi? Or what's halfway between 0 and positive 2 pi? Pi. So our points of inflection, we would have 1 at pi, comma, what's our d? 1. You could have 1 there. You could have a whole bunch. So again, the formula would look like this. You take your starting point, which is a pi, and the period changes the x. So I would do it plus 2k pi, comma 1. That would be all. This is a point of inflection. That's 1 point right there. That's 1 point. This is all points of inflection right there. Now, where is it concave up? Let me show you. If we were to graph this real quick, this is a negative 2 tangent. That means it's a tangent that decreases like this on its domain with those asymptotes that we already found at 0 and negative 2 pi and positive 2 pi, like that. So what's going on over here? Is this concave up or concave down on this side of the point of inflection? Concave up. What's happening on this side? So from 0 to pi, it's concave up. From pi to 2 pi, it's concave down. And so again, just one interval would be concave up, we said is 0 to pi. Remember, intervals mean you list x values, not y's. Those are both x values. Concave down is from pi to 2 pi. So by formula, all you would do is add 2k pi to each. So any 0 plus 2k pi is 2k pi, comma, pi plus 2k pi. That would be all intervals of concave up. All intervals of concave down would be pi plus 2k pi, comma, 2 pi plus 2k pi. It's getting confusing to write that, but that's how you'd write that. Again, that's a interval, all intervals. All intervals, a interval. All right, let me do one interval like I did before. One interval. Okay, so there's like basic information on it right there. You can go back to the very front. You can go back to the very front. If you needed to look at some of the rules, you can also kind of look at this. This is just a general way of putting it together. All right, with that, do well. Number 3. And now, example 5. Let's go backwards. Given a graph, could we figure out asymptotes, points of inflections, and figure out the following? Let's try it. Asymptotes. I'm going to use a tool to help us out here. All right, picking up here after the interruption. So we have an asymptote at negative pi over 4. This would be 3 pi over 4. 9 pi over 4 if I'm doing math right in my head. And this would be negative 5 pi over 4. So those are our asymptotes there. If I look at the period, I can see there are 4 blocks apart. That would be 1 period. So an easier way, once I know how many blocks it is to count 4 blocks from 0, which is pi. My period is 1 pi, which the period can indicate to you what the b value is. Because remember, pi divided by b has to equal my period. So my period is pi. So I can multiply by pi, b, multiply both sides by b here. And now I know pi equals pi b, and then I would come back and divide by pi. And so when I divide that by pi, pi divided by pi is going to be 1. So b equals 1, because those cancel out. That's our b. B is 1. That doesn't make sense what I just did there, so I'm going to take some of that away there. But that's what I would do last, is I would divide by that as well. Okay, so b is 1. Pi equals pi b, and I'll do it right here. So you can see it yourself. That's an easier way of seeing what's going on. So pi b would be 1. Okay, points of inflection. So if you split the difference, I have points of inflection here, here, there. I'll go off this first one. This is halfway to pi over 2, which means I'm at pi over 4. The x value for the points of inflection start at pi over 4. And it repeats every 1 pi. Remember, the period is 1 pi, so I want to do plus k pi. Now, my d value has to be a value of 2 because I'm up 2. So d is 2. All right, so there's my points of inflection. You should say points of inflection. That would be all of them. And my d is 2. Picking up from there, how can I find my y, my a's? Well, my a point, remember, if you split this difference, that is a positive a because I'm increasing, and it looks like it's a half. Those are my a points. This one is down a half going this way. So a is a half. C is how far is it shifted left to right. Now, my asymptote was supposed to be pi over 2. Instead, I got shifted right to 3 pi over 4. Notice I got shifted 1 block, which we said was pi over 4. mine must have a negative pi over 4 because I went right pi over 4. So remember, everything's opposite. So now put it on the inside. So my equation must be y equals a first, a of 1/2 tangent bracket. My b is 1. I actually don't need to bracket since b is 1. I'll just do parentheses. X minus pi over 4 plus 2. That would be my equation for this function. Now that we've done that, it comes to DOL number 4. All you have to do here is match up the graphs. I've given you 4 equations, A, B, C, and D, and I want you to look at these 4 graphs and try to match them up. 1 equation per graph. DOL number 4.